This lecture is on chapter 7.6 to 7.8 on oxidation reduction reactions and activity series. So recall the introduction that we had for oxidation reduction reactions or redox reactions, which are processes which involve one or more electrons to be transferred between reaction partners, either atoms, molecules, or ions. All right, so let's get into this in more detail. So oxidation is defined as the loss of one or more electrons by a substance, whereas reduction is defined as the gain of one or more electrons by a substance. Okay, so these terms seem a little bit confusing at first if you think of reduction as being a gain of electrons. So let's think about where this name reduction comes from. So if you think about positive charge as being plus, negative charge as being minus, if you gain an additional negatively charged electron, what you're doing is you're decreasing the overall charge by adding a -1 charge. So you can think of reduction as gaining a negatively charged electron. Okay, and oxidation, the fact of losing one or more electrons, oxidation usually happens in the presence of oxygen. So we can see here, regardless of which sort of state you start with, whether you have a 2 minus, 1 minus, a neutral, or a cation here, you can undergo oxidation reactions from left to right, or you can add an electron to go through reduction. So any species can be oxidized or reduced. So let's look at a specific example here. We can see that iron can be oxidized by oxygen to form Fe2O3, which is rust. So it's a very common reaction that we see quite often. Whereas rust can be mixed with carbon to reduce rust back to iron and carbon dioxide. Okay, so we can either oxidize or reduce a material depending on how we actually react with them. Okay, and so in the next few slides here, we're going to overview how we can actually recognize these as an oxidation or reduction reaction. So why does a specific material either oxidize or reduce when it is in the presence of a different species? And so to understand that, we need to bring back the idea of electronegativity. So recall, electronegativity is one of our hallmark concepts in general chemistry that keeps coming back over and over again. And so electronegativity, remember, is the tendency for a bonded atom to attract electron density towards itself. And furthermore, we have non-equal sharing of electrons in covalent bonds. You can have non-polar covalent bonds where the electrons are equally shared between the two atom atomic centers, or you can have a polar covalent bonds where the electrons are they're unequally shared, and the electron density locates itself around the more electronegative atom, and there's an electron deficiency or a partial positive charge around our less electronegative atom. Okay, so we have this idea, and the way to predict whether a bond will either be polar or nonpolar is dependent on the specific electronegativity of each of the involved atoms. So let's take this same sort of idea of electronegativity, the tendency of a specific atom to attract electron density. So let's think about that in terms of oxidation and reduction. So chemical reactions that involve a complete transfer of electrons. So we can assign what are called oxidation numbers to each atom in a specific molecule. So electron density resides primarily with the more electronegative atom. We see that in our polar covalent bonds. So the oxidation number, or the oxidation state, is a value that indicates whether an atom is either neutral, electron rich, or electron poor within a specific molecule or ionic compound. So if you have a negative oxidation number, that means that you have more of a negative charge, which means you are electron rich. If you have a positive oxidation number, that means that you are having a smaller number of these negatively charged electrons, which means you are electron poor. If you have a zero oxidation number, that means that you are electrically neutral and you're your ground state electron configuration, where you're not pulling any larger or smaller amount of electrons. And so this is similar to the trends used for ions versus atoms. So what are the rules for assigning oxidation numbers? Okay, so our first rule is that an atom in its elemental state has an oxidation number of 0. So if we take a look at some of our commonly found elements, we can see that sodium in its solid state, iron in its solid state, a lot of our metals in their solid states, and we have our diatomic gases like H2 gas. We have our bromine liquid, Br2, chlorine gas, oxygen gas, neon gas, all of these different elements. If you think of elements, carbon, solid, any element that is present in its baseline stable state is going to have an oxidation number that we call 0. So we can put a superscript 0 above those to indicate their oxidation numbers of 0. And so what that means is that they're neither electron rich or electron poor. They are just in their regular ground state. Number 2, an atom in a monatomic ion has the oxidation number identical to its overall charge. Okay, so if we take a look at, for example, the sodium ion, Na+, or the calcium 2+ ion, or aluminum 3+, O2-, Cl-. All of these cations and anions have an oxidation number equal to its overall charge. So the oxidation number for sodium is a +1, oxidation number for calcium is +2, aluminum +3, oxygen -2, chlorine -1. So very straightforward. Number 3, an atom in a polyatomic ion or in a molecular compound usually has the same oxidation number it would have as if it were a monoatomic ion. So oxygen usually has an oxidation number of -2. Halogens, which is our group 7A, usually have an oxidation number of -1. Hydrogen can either be +1 or -1. And so the way we determine for hydrogen whether it's +1 or -1, if the hydrogen bonds to a nonmetal, it's going to be a +1. If the hydrogen bonds to a metal, it's going to be -1. So let's take a look at the examples that we have here on our slide here. So we have first H2O. So our hydrogen bound to an oxygen, bound to another hydrogen. All right, so we know our oxygen is going to have the oxidation number most similarly to as if it had if it was just the O2- ion. So that's going to have a -2 overall oxidation number. And so since oxygen is a nonmetal, we know that these hydrogens are each going to have a +1 oxidation number. Okay, and so I believe we'll get to this in a later rule here, but all of the oxidation numbers for a specific molecule have to add up to equal the overall charge on the molecule. And so since there is a 0 overall charge on water, +1, +1, -2 all add up to equal 0. Next, HCl, a hydrogen and a chlorine. So we know that chlorine is going to have an oxidation number similar to as if it were just a regular ion. So that's going to be a -1 oxidation number. And since chlorine is a nonmetal, we know that we have a +1 for our hydrogen. And since HCl is neutral, +1 with a -1 equals 0. All right, lastly, we have CaH2. And we know that calcium, if it were an ion, would have a +2, so that gives a +2 oxidation number. And since calcium is a metal, That tells us that our hydrogen in this case has to have a -1 oxidation number. And we add all those up together, we get our total overall charge of 0. Next, rule number 4. The sum of the oxidation numbers is 0 for a neutral compound and is equal to the net charge for polyatomic ions. Okay, so this is the rule I just told you in the last slide. So let's work through again. So H2O, we know that this is electrically neutral. Oxygen carries, so actually, let's pause for a second and see if you can actually work through all of these on your own. And pause the video and then log back in and then see if your answers will match up. Okay, so oxygen, we know in its ionic state would be a 2-, so we're going to say oxygen has an oxidation number of -2. And since oxygen is a nonmetal, we know each of these hydrogens are going to have a +1, so a +1 and a +1 for our two different hydrogens. Overall, we have an oxidation number summation of 0. Next, OH-. All right, so we know that our overall summation of our oxidation numbers has to equal -1. We know oxygen is -2. Oxygen's a nonmetal, so therefore the hydrogen is a +1. -2 + 1 equals -1, which is our overall charge. Next, H2SO4. All right, so we know the overall charge here has to equal 0. We know our oxygen, each of our oxygens are going to be equal to -2. So if we have 4 of our -2s, we're going to have a total oxidation numbers for our oxygens, -2 times 4 of -8. We know our hydrogens are each going to be +1. So +1 times 2 gives us a +2. And we know the overall charge has to be 0. So that tells us then our sulfur has to have an oxidation number that's going to allow us to add all these up to 0. So therefore, our oxidation number for sulfur has to be +6. So 2 + 6 - 8 equals 0. Okay, finally, for Cr2O7, 2-, our overall summation has to equal -2. We know each oxygen is going to carry a -2, and we have 7 oxygen, so that gives us a -14 overall. So we have to, when determining our chromium here, we know that these two chromiums have to add up for our summation to equal -2, which means that our overall has to equal a +12, which means that each chromium must have a +6. Okay, so because our summation of all of our oxidation numbers have to equal the overall charge on our molecule or our ion. Okay, so take a moment here to work through these different examples for and assign oxidation numbers to each of the following compounds. Okay, iron is an element in its baseline stable state, so therefore it's going to have an oxidation number of 0. O2 is an element in its baseline stable state, therefore each of these oxygens are also going to have an oxidation number of 0. So this is a case where oxygen does not carry a -2 overall charge. This is its elemental state, so each oxygen has 0. CH4. Okay, so each of these hydrogens, so the hydrogen is bound to carbon, which is a nonmetal here. So we know each of those hydrogens are going to have a +1. The overall charge here is going to be +4 because we have 4 hydrogens. So therefore, our carbon here has to be a -4. Next, LiH. So lithium we know is an alkaline metal, so that's going to have a +1 oxidation number. And since lithium is a metal, we know our hydrogen here is going to have a -1 oxidation number. All right. K2CrO4. Potassium is an alkali metal, so each of those are going to carry a +1. So since we have 2, we have an overall +2 oxidation number. Each of our oxygens are going to carry a -2. Since we have 4, we have -8. And we know the overall charge on this salt here is going to be a 0. So we know that this chromium here has to add with our other oxidation numbers to get 0, which means that we have to be a +6. Finally, NaCl. This one's quite easy. We can see that our alkali metals always carry our +1, and our chlorine carries a -1. Okay, so now that we've gone through how to actually assign our specific oxidation numbers, now we can go through the idea of oxidation or reduction reactions, which are the gain or loss of one or more electrons by a substance. So we can observe an oxidation occurring if we see an increase in the oxidation number, which means we have less of these negatively charged electrons. Whereas a reduction we can see as a decrease in our oxidation number, which means that we have more of these negatively charged electrons associated with a specific atom. So identify which species are oxidized and which species are reduced on the following reactions that we had previously for the formation of rust and the chemical decomposition of rust. So take a moment to go through that on your own. Okay, so for our first equation, we have 4Fe solid plus 3O2 gas gives us 2Fe2O3 solid. So we know that our iron is in its elemental state, so that's going to have an oxidation number of 0. O2 gas is in its elemental state, so I'll have an oxidation number also of 0. And then Fe2O3 is an ionic salt. And so we're going to have oxygen is going to have its oxidation number of -2. And then since this is iron 3, it's going to have our oxidation number of +3. So what we can see now is that this iron goes from 0 to +3, and the oxygen goes from 0 to -2 oxidation number. So now we need to identify which species is oxidized and which is reduced. And so oxidized means we have an increase in our oxidation number, which means we are decreasing the amount of electrons associated. So this iron, we can say that the Fe is oxidized. And for every oxidation, there has to be a reduction. And we can see that the oxygen going from 0 to -2 means that there's a reduction occurring, which states that the oxygen is reduced. Next, we can see that for the second reaction, we have 2Fe2O3 solid plus 3 carbon solids yields 4 iron solid plus 3 CO2 gas. So let's assign all of our oxidation numbers. Fe2O3, just as for the last example, we have a -2 for oxygen and a +3 for the iron. For carbon, we're in an elemental state, so we're at 0. We go to iron in elemental state, which is 0. And CO2, we know each of our oxygens are going to be -2. And 2 times 2 equals -4, so therefore our carbon is a +4. Okay, so if we take a look at our oxidation or reduction, we can see that the carbon goes from an oxidation state of 0 to now an oxidation state of +4. We see our oxygen stays at -2 the whole time, but our iron goes from a +3 down to 0. So we are decreasing our oxidation number for iron. And so decreasing oxidation number means we are going through a reduction. So this states that the iron is reduced. Whereas our carbon, going from a 0 to a +4, is increasing the oxidation number, which means that our carbon is oxidized. So I previously stated that an oxidation cannot occur without an accompanying reduction. And vice versa. Reduction can occur without an accompanying oxidation. And so this introduces another term called an oxidizing agent or a reducing agent. So a reducing agent causes reduction, which and it loses one or more electrons, and it undergoes oxidation. And so the oxidation number of the atom increases. Whereas an oxidizing agent causes the oxidation of a separate species, it gains one or more electrons, which means it is reduced. And so the oxidation number of the atom decreases. So to the take-home message here, the reducing agent is the species that causes the other reactant to undergo reduction. And that species itself, the reducing agent, is oxidized. The oxidation agent is the species that causes the other reactant to undergo oxidation. And so that oxidizing agent, undergoes reduction. So if we take a look at those same reactions before, we observed oxidation and we observed reduction. We observe oxidation, we observe reduction. Pause the video for a second to identify the oxidizing, and reducing agents. So you can see here that for our first example, the iron, which is being oxidized, is the reducing agent because it is causing oxygen to undergo reduction. Whereas the oxygen, O2, is the oxidizing agent because it's causing iron to undergo oxidation. And that oxidizing agent undergoes reduction. In the second reaction, we see carbon is the reducing agent because it causes the iron to undergo reduction. But the reducing agent undergoes oxidation. Iron is the oxidizing agent because it causes carbon to undergo oxidation, but the oxidizing agent iron undergoes reduction. All right, so the oxidizing agent's reduced, the reducing agent is oxidized. So why do we care about this? Why are redox reactions important? And so the short answer is that these redox reactions show up all over the place within our daily life, and they are absolutely key for our existence as humans. And so one very fundamental example of how redox reactions actually take place in all living species is cellular respiration. And so aerobic cellular respiration occurs through a multi-step process involving glycolysis, the Krebs cycle, and the electron transport chain. So the overall process that's detailed in this equation down here on the bottom is a redox reaction, where the reaction energy is stored as high energy ATP molecules, which are used to power our bodies. And so we have glucose reacting with water to give us carbon dioxide, water, and energy. So if we take a look at this cellular respiration, this is actually an oxidation reduction or a redox reaction. So if we take a look at our specific oxidation numbers here, we can see that our oxidation number for oxygen here is -2. So -2 times 6 is -12. We have our hydrogen, which is a +1, so that'll be 12 of those, so that's +12. So combine the hydrogen and oxygens together in glucose, we can see that those oxidation numbers equal 0, which means our oxidation state for carbon is also 0. And we see for oxygen here that this is our elemental state, so our oxidation number for oxygen is also 0. And then the product, carbon dioxide, we know oxygen's -2, so therefore this carbon is a +4. So where carbon goes from 0 to +4, which means it's oxidized. Whereas H2O, or H, is a +1, same as over here. But our oxygen here is a -2. So we go from a 0 oxidation state to a -2, which means that oxygen is being reduced. So we have an oxidation and a reduction both occurring in this key equation for cellular respiration. So without this redox reaction, all life as we know it on Earth would fail to exist. So redox reactions are incredibly important. All right, the final concept I'd like to cover in today's lecture is that of activity series. So if we have how can we predict which specific oxidation or reduction reactions that we expect to occur? So if we mix together silver solid with copper 2 plus, we have a predicted chemical reaction. And if the same sort of, if we flip that, if we mix copper solid with silver plus, we would expect the reverse of that reaction to occur. Okay, so the top and bottom reactions here are just flipped direction of the same reaction. So how do we predict which reaction will actually occur? The forward, the equation 1, or the reverse, which is equation 2? So experimentally, we can see that if we place a copper wire in a silver plus solution, we can observe that the copper leaches out of that wire, which turns our aqueous solution this bluish color, and we can see a deposition of our silver solid on the specific metal. So showing that our reaction 2 is actually occurring. So experimentally, we can see this happening, but how can it be nice for us to be able to predict which one of our redox reactions will actually dominate, and so which species will be oxidized and which will be reduced? So this brings us to the activity series, which is the table listed here on the right, which shows a series of oxidation reactions for a bunch of different species here. So we have these specific atoms here that are losing an electron. And so if we reverse all of those equations, we would see the reduction reactions. And so elements that are listed higher on this list are more likely to lose an electron and oxidize, which means they are more strongly reducing, whereas elements lower on the list are less likely to lose an electron, and so they are weakly reducing. So any element that's higher in the activity series will reduce the ion of any element that is lower on the activity series. So if we take a look here, we can see if we look for copper, so copper and silver are two elements that are involved in our top reaction here. So since copper is higher on the table than silver, that states that copper will reduce the silver, okay? Because the element higher in the activity series will reduce the ion of any element lower in the activity series. So the copper will reduce the silver plus into silver. All right, so the higher is going to be the reaction going from left to right, and the lower is the reaction going to be going from right to left. All right, left to right on the top, right to left on the bottom. Okay, and so you can use that for any reaction pair using the activity series. So, your turn. Use the activity series on the right to determine which reaction will not occur. Okay, so take a moment to look through that. Okay, the correct answer here is D. So let's take a look at each one. So we have calcium solid. So we find calcium on our table. So up here towards the top. And copper 2 plus. So we're seeing which reaction will not occur. So we know calcium is on top. So that reaction is going to go from left to right. Copper is on the bottom going from right to left. So calcium and copper are going to react. Calcium and zinc. So we see calcium up here and then zinc. So calcium's going to go solid from left to right. Zinc is going to go 2 plus from right to left. So calcium solid with zinc 2 plus. That is going to occur. C, zinc here and copper. So zinc is higher, so we're going to go left to right for zinc. Copper is going to go right to left because it's on the bottom. So we have zinc solid and copper 2 plus. Zinc solid, copper 2 plus. Zinc and magnesium. So magnesium's up here, zinc is down here. So since magnesium is higher, it's going to go left to right. So magnesium solid. Zinc is lower, so it goes right to left. So that's zinc 2 plus. So magnesium solid, zinc 2 plus. Here we have the opposite, zinc solid and magnesium 2 plus. This D reaction will not occur. All right, with that, I will leave you to this oxidation number worksheet. That's it for the day. Thank you.